So I studied control systems for a couple years. Mostly I'm a programmer, but I have a degree in electrical engineering. Anyway, so I'm going to show you rocket science, which is you give a feedback. You select a feedback gain for the rocket, and this example uses a run-kutta integrator. Basically, the physics engine is what an amateur uses is Euler. We're going to look at Euler in a second. First, I want to show when you're doing control systems, you do a lot of work in the complex plane. You have poles and zeros. These are complex numbers, and if we hit the phase, anyway, these are zeros. If you put a zero on top of a pole, it cancels it out, but you can't really do that because you can't get it exact. Anyway, when you study control theory, what you're worried about is poles in the left half plane. If it's in the right half plane, it's unstable. These are complex conjugate pairs. So in control theory, you look at pole root locus. You study how these move around when you change. You have a feedback gain, kind of like turning up an amplifier. And as you turn it up, the poles move around. And if you turn it up too much, then it goes into the right half plane and you get feedback. And that's what you worry about. Anyway, that's classical control theory. We're going to look at, mostly you study linear systems, but the nonlinear is a lot more fun and it's real world. This is a predator-prey problem. It's not using an integrator, it's using Euler. Euler is basically what an amateur does, which is basically you take steps and you add the derivative. So this is predator-prey, hawks and rabbits. So we just have we take tiny steps, and we have a differential equation. This is a nonlinear differential equation. So we have hawks times. Oh, hold on a second. Okay, yeah, it's nonlinear because we have x, y. We have, normally you might call these x, the population of hawks is x, population of rabbits is y, and we have a cross term here, hawks times rabbits. The derivative of hawks is when there aren't enough rabbits to eat, the hawks start to die and stuff like that. Anyway, it's so what you get, this is a I think they call this a phase plane plot. You plot the population along with the derivative. It's kind of a strange, but it's a standard approach to nonlinear differential equations. So the system moves around in circles based on what the initial number. Let's say you had 100 rabbits, it would go in one set of circles. If you had 10 rabbits, it would go in another circle. They're called limit cycles. The system spins around, and we're using, this is a good example for showing off my operating system because it's simple. We're doing multi-core parallel processing to get this done. So let's look at the program, turn off the autocomplete, set up the screen. We draw the axis. Then we wait for a character and we stay in a loop, and we set flags for the multi-cores. We're gonna assign a job to each core, and down here we wait until all the cores finish. So yield means swap in the next task, and it's waiting until all we set a bunch of ones. Like if there's 8 cores, there's 255 is the value, and then we clear all those bits down to 0, and then it's ready to go again. And then what it does is it assigns a job to each core, plot trajectory. So there's each core does this function, and this function does 1,000 steps, plotting red and green, and each step is actually a bunch of micro steps. Anyway, basically, and this is the derivative in here. So it's the nice thing is it's all transparent. A lot of programs you'll find they'll plot the graph for you, but it's simpler if you can just do it yourself. So basically you plot the graph just like you want it, and that way you don't have to learn a framework and stuff. Anyway, so we can try other did you know that you can make up brand new functions that can't be written with transcendental functions from differential equations? In other words, we can make something never before studied by, let's see what we get here. Well, anyway, you can just throw some, let's say, how big is this? How about times sine of rabbits? So you might, I like to, it makes me feel very, I love this. We can make brand new math that has never before been seen. This stuff has never been seen. So you can get functions that never been seen before. Anyway, so I asked God the most interesting ecology or something problem. He said pollen. So you can imagine, what if you did the entire ecosystem, and you have trees that give pollen. Let's say you have maple trees and oak trees and flowers, and you have bees that go around and pollinate, and then you have herbivores, and it gets really, how would your differential equation look for different flowers getting pollinated with bee populations? That would be pretty cool. I love nonlinear differential equations. I just like them. Anyway,